So hello everybody. Can you hear me well? Yes. So uncomfortable. All right. So let me thank the organizers for inviting me here today. I'm going to talk about, well, that's a very general title, but I'm really going to focus on the H-0 tension between Planck and direct measurements, and whether I'm going to update you about the work that has been done in these last months in particular. But let me start by saying that one of the takeaway messages, I would say, of the Planck mission is that the lambda CDM model describes extremely well the CMB data. We have an excellent chi-square for our power spectra. We find no deviation or no significant deviations from lambda CDM when looking at extensions. And we can measure basically cosmological parameters, most of them at the percent level. And I think it's really remarkable that when you compare them with other astrophysical data sets, we have an extremely good agreement between very different measurements. And even though, even with those that do not work very well, we have consistency at the level of 2-3 sigma. There are a few data sets that work extremely well that tell us the same story as Planck, in particular BAO, supernovae, and BBN. Well, direct measurements of primordial elements. We have some tensions on the sigma 8, omega n parameters from cluster counts and weak lensing. Not going to talk about these data sets with you today, but I'm happy to discuss this offline. And we have a difference in the measurement on H0, so between Planck and the direct measurements from supernovae calibrated with Cepheid's data. This is a very interesting difference, is at the level of the 3 sigma. And it's interesting because the direct measurements are really measuring H0 very close to today, while the H0 measurement from the CMB is an indirect measurement. So the interesting part about this is that potentially if there is a difference between these two values, this might be the indication of a failure of lambda CDM and the need of extensions of this model. However, you realize that before claiming extensions of lambda CDM, we need to make sure that we understand extremely well the systematics in the direct measurements and make sure as well that we don't have systematics in the CMB data. So I'm going to just mention a couple of things I want to tell you about these first 2 points, and then I'm going to concentrate on the third one. So about extensions of lambda CDM, people have worked or have tried different models in order to see whether it is possible to alleviate this tension by extending lambda CDM, playing, for example, with dark energy parameters, or extending to extra number of relativistic species. One thing that I want to tell you about, however, today is that there is no easy extension of the lambda CDM that can basically fit all the data available. And here we're not talking about only the CMB or the direct measurements, but also we're talking about BAO, supernovae, and so on and so forth. And there are further details, for example, in these 2 papers here. And one very common example is, as I said, this number of relativistic species. And I just want to make the point that, so Planck, in the lambda CDM case, has H0 around 67. And what extending to number of relativistic species does is just increasing the error bar. But the average or central value of H0, it's still centered to low values. And this is just because Planck is in extremely good agreement with the hypothesis of the center number of relativistic species. So what you are doing when extending the model in this way, you are just increasing the error bars on one side, and you are combining with the data set that is in tension, and then if you combine these 2 data sets, you will have extra number of relativistic species. I think no one of us would believe this result just by playing this game. On the other hand, what about systematics in the direct measurement? As you know, direct measurements are built, these are distance ladder measurements. You have supernovae. Well, in the Hubble's law, you want to measure distances with the distance magnitude relation that you want to calibrate with Cepheids, with the Leavitt law. And then you want to calibrate the Cepheids by local measurements of distances to close Cepheids. So there are a number of different steps, and if something goes wrong in one of these steps, you might you might have an error in the inferred value of H0. Now, the very interesting thing is that since the data set from Rees et al. Came out last year, there has been a number of different papers really testing for different systematics. So what happens if you do different cuts for the Cepheids data. In particular, this work here is very nice because it was blind. So basically they decided all their cuts before knowing basically the value of H0. And then they unblinded, and all of these different analyses still get H0, which is in very good agreement with what Rees et al. Finds, with some variation, say, in the error bars. But essentially, they still find high H0. So what about this possible systematics in the CMB? So here I show, again, this is the value of H0 from Planck combined with the low L polarization from HFI that we published last year, compared to Rees et al. Again, is a 3 sigma tension. And this is a tension that we also have had back in 2013 with the first Planck release compared to the Rees et al. Results of 2011. And, at first people were like, oh, there is this tension, but Planck is not the only data set, CMB data set that we have. We also have WMAP, SPT, we have ACT, sorry, I didn't put it here. We have other measurements, and this two gives you somewhat larger values of H0. Sorry, Lyman, sorry. When you realize that it's a big mistake in the talk. I'm very sorry. But so you might wonder, okay, but maybe there is a problem in the Planck data, and WMAP and SPT are right, are in better agreement with the direct measurements of H0. And I want to give you 2 reasons why this is actually not true. So the first one is that these are large error bars. For example, WMAP is the error bar from WMAP is say more than twice the one from Planck. So for example, you want to combine with other data sets in order to decrease this uncertainty. So for example, if you combine with BAO and high redshift supernovae, you also get a low value of H0 in tension with Rees et al. And the same thing if you add, in addition, the high L experiments. So this is the very interesting thing, I think, about this tension, is that possibly this is not a Planck versus direct measurements tension. This is more widely a CMB versus direct measurements tension. The second very easy reason why it's not evident that there is a problem between Planck, WMAP, and SPT is that if you do the job properly, you actually see that these 3 experiments are in good agreement. So why do I say this? You have to, bear in mind when you look when you look at results from these 3 experiments. And sorry again, I'm concentrating on SPT and not on ACT. Is that Planck and WMAP are full sky experiments, but with very different resolutions. In particular, WMAP is cosmic variance limited until multiples of L of about 600, while Planck has an enormous signal to noise till L's of 1600. So we measure a lot of additional modes that gives you statistical power, and in some way you don't expect that results from these two experiments will perfectly overlap. So what you can do is comparing, for example, these two experiments in a multiple range where the signal to noise is more comparable, and you can see, for example, that on H0 we have similar results. On the other hand, with SPT, the problem is that SPT also only observed 2,500 square degrees, so a very small patch in the sky that we have to compare to the full sky of Planck. And there are these two very nice papers comparing the Planck data, but now only in the patch of SPT, and they also find that there is a better agreement, especially on NS, between SPT and Planck. I'm not going into the details of this, but just to say that doing this properly requires a lot of work. But still, what we wanted to know internally in Planck, we are working really hard to understand, to really understand whether we have a problem or not. But one of the questions that we had was understanding whether this shift, so when you cut Planck, for example, at a max of 800, is consistent with what we get with the full baseline. So what we did was very simple idea, but long to do, and Marius did a really great job on this point. So we simulated TT power spectra, calculated cosmological parameters from these two cuts, but we also tried all possible different cuts. Here I'm showing you these two just because this is more comparable with what you get with WMAP, and this is comparable with what you get with the full Planck, but you can do, L max of 1,000 versus L mix of 1,000, and with all different possible choices of L. And we just compared the shifts in parameter that we get from the data with the simulations. And this is the result of this work. So what I'm showing you here are the cosmological parameters, and these are the differences in, for example, H0 that you get from this Lmax 800 range and Lmax 2500. The blue points are the simulation, the orange lines are the data. And what's interesting is that you can see that for some parameters you lie, it seems to lie close to the 2 sigma contours, but at the same time you also always lie along the degeneracy lines. And so this is why basically the significance of each of these points, when you take into account all the 6 cosmological parameters, it's not very high. What do I mean by that? If you calculate the chi-square of the parameter of these parameter distances, where your covariance is just directly calculated from the simulations, you find that the chi-square for the data has a PTE of 15%, which is equivalent to 1.4 Gaussian sigmas. So, from the point of view of are the low L, low intermediate L's from Planck consistent with what the high L tells us, from this work the answer is yes. We don't find, with all the possible cuts that we've tried, we don't find that these differences are significant at more than 2 sigma level, ever. However, this was the first part of the paper we published last year, but the second question was really, where do these shifts come from? And we identified two reasons why the high L prefer like a lower H naught compared to the lower multiples. So one is this preference for extra peak smoothing at high L that you can call lensing, extra lensing, but it's not lensing. It's just the peaks seem to be a little bit more smooth compared to what you would expect in lambda CDM. This can be fitted with, say, a phenomenological parameter, which is this A-lens parameter, that for Planck is a couple of sigma high compared to what you would expect. And so this is the first reason, and the second reason is the fact that Cora showed that basically at large scales we see that these points lie a little bit low compared to the best fit lambda CDM model. And what's the impact of these two effects that we think together can explain the difference between the low and the high L parameters from Planck is the following. So this is the baseline for Planck on H naught. This is L max of 800, the high value of H naught. If you also allow basically the data to be fitted by this A-lens parameter in addition to the lambda CDM parameters, you can see that you go halfway from the value of the low L H naught compared to the baseline, but this is not enough to explain completely the shift. We think that the second half is rather done by cutting out these low L multiples that seem to be a little bit too low at large scales. So basically you go from here to here. This is a huge, well, it's a pretty large shift when you only cut out the first 30 multiples. So why, you can see that this is cutting out these first multiples is very effective for the Lmax 800. Why? Because here you don't have a lot of leverage, and these first multiples are very useful to constrain NS. Well, when you have the full Planck baseline, you have a very long lever arm, and cutting out the first 30 multiples do not do very much to your results. All right, so just to conclude, the Planck results are consistent with a number of different data sets. There are open issues with a few data sets in particular, the measurement of H naught. This is probably not only a Planck tension. This is more broadly a CMB tension with the direct measurements. And there has been a lot of work to assess the consistency between Planck and other data sets, in particular lately with SPT, and there is good consistency between these different data sets. We think that the low and the high L's from Planck are, again, in agreement, and we think we also have identified the reasons why the two are different. And we are working hard on the third release for Planck, so stay tuned.